This is lecture 9.2. It's the continuation of our discussion of autocorrelation. This week, or this lecture, we're going to learn how to test for autocorrelation. So grab your pen and your paper and we'll get started. All right, I just need to make sure my camera's in focus. You will be pleased to know that this will not take long. We're going to learn how to test for autocorrelation. And now the thing is, what I could do is go through all the material in the chapter, which covers, there is the Durbin-Watson test, there's the Box-Pierce test, there's the Leung test, and there's the Durbin-H test, and there's the, I'll just call it the LM test, the Lagrange multiplier test. It's also called Bush-Godfrey. And in presenting all of these, the textbook points out, so the Durbin-Watson test, it's only useful for testing for AR1, and it's often inconclusive, so it's not a very good test. The Box-Pierce and the Young test, they don't have that problem, but they're also only suitable for AR1. Well, no, they're more general than that, but they're not suitable if you've got certain types of regression models like lag-dependent variables, so they're not reliable for that. The Durbin-H test, I first learned the Durbin-H test when I was in 4th year. And at the time they presented it, my professor presented it and said, there's this Durbin-H test, and here's how you do it. But nobody does it because it's not a very good test. And yet it's still in the textbooks. They always present it. The LM test is always applicable. It has good test performance. In other words, it gives reliable answers. And you can use it for any form of autocorrelation. So what I'm going to do is I'm only going to show you the LM test. If you want to learn about the Durbin-Watson test or all the others, they're in the textbook, and you can look them up, but they're there kind of for historical reasons. So that's why this doesn't need to take too long. So the LM test. What does LM stand for? It stands for Lagrange multiplier test. And that refers to how the test is derived. It's derived as a constrained optimization problem. So just looking through the book here, testing for autocorrelated errors. In the discussion, so it refers to likelihood-based testing and using likelihood ratios which come from maximum likelihood estimation. And we didn't cover that, so we skipped likelihood ratio tests. So this paragraph here on page 145, you'll find that it may be kind of hard to understand what he's talking about. So just start from the second paragraph in this section. The Lagrange multiplier approach to testing. So here's how it works. The LM test. So first of all, step one, you would regress y on the x's, and you get your residuals. So you get the residuals. Second, regress the residuals on the x's and the lag residuals. Just one, we'll just add one lag in, and get the r squared from that regression. And then we construct t, which is the sample size, times r squared, and that's our test statistic. And it's distributed chi-squared with 1 degree of freedom. The null hypothesis is there's no autocorrelation. And in that case, under the null hypothesis, r squared equals 0. If you take the residuals from a regression and just regress the residuals on the x's, you always get an r squared of 0. Just because of the way regression works, the residuals, it's the part not explained by the x's, so you get an r squared of 0. And all we've done here is add in the x's and the lagged residual, so it kind of makes sense that if there's no autocorrelation, then that r squared will be 0. So if this is a big number, we're taking t times the r squared. If this is true, then this will be 0 as well. If we get a large number, though, then that means we probably have autocorrelation. So this is the form of the test for AR1. So that tests AR1. If we want to test for higher order autocorrelation, testing for higher order autocorrelation, then step 1 is the same as before. Step 2, you can probably guess what step 2 is going to be. We'll regress the residual on the x's and various other lags. So epsilon t minus 1, epsilon t minus 2, and so on out to epsilon t minus p. So you can add in as many lags of the residuals as you want to test. Now bear in mind, the more lags you add, you lose an observation at the start of the regression. And then t times r squared will follow chi-squared with p degrees of freedom. So when you add another lag in there, you have to change which table you're using. So that is the LM test. And then the rest of this section in the book, so that's the one that you're actually going to use in your assignment. And then we've got Box-Pierce and the Young tests. And as it says here, it's a warning, doesn't always work. Durbin-Watson, then Durbin-Watson is calculated using that formula there, but we don't know the distribution of the Durbin-Watson test, so there's special tables for it, and the tables don't cover all the possible outcomes, so it could be you calculated it and it's indecisive. Again, that's not a problem with the LM test. And then there's Durbin's H test, and it's listed here, and but the problem with the H test is sometimes it doesn't make any sense because it gives you an outcome where you're calculating the square root of a negative number. So we shall not bother with those tests. There you go. I think that's the only time I've done an entire lecture on a single page, but that's all I need to tell you. For the assignment, you're going to calculate the LM test, but you're going to use you have to use a package. Let me just look up while you're here what that package is. All right, so it's assignment 4. I'm just opening it up here. So it is the BG test command from the LM test package. So now I'm going to stay on the same page just so I can say that I did a lecture on a single page. So it's the LM test is the name of the package because it's implementing a bunch of Lagrange multiplier type tests, and you're going to use the bg test command. And it's called bg because what I just showed you is also known as the Bush-Godfrey test. Same as Bush-Pagan, same guy, clever guy. But this was the test for autocorrelation, not heteroscedasticity. So it's the bg test command. What goes in the brackets? Well, if you know how when you do a linear regression and you'll call it, let's say it's your first model, so you call it M1 equals LM, and then it's Y regressed on X1 plus X2. Well, you're just going to plug bg test M1. And isn't that easy? It'll do all this stuff for you. And it'll, as a default, it'll do the AR1 test. But if you want it to test higher order terms, then you just add an extra option in there for the testing the higher order terms, whether you want to go 2 or 3 or however many legs you want to do. But you're just going to use the bg test command, and it'll calculate the test statistic, and it'll also give you the p-value of the test statistic. So then if it's smaller than 0.05, you'll know you can reject the null hypothesis. And if you reject the null hypothesis and you've got an autocorrelation issue, then you can either do an AR1 correction or you just opt for Nui West standard errors. But in the assignment, and I guess I will have to go on to another page here, I'm going to give you a hint for the assignment. Because sometimes what looks like autocorrelation is actually model misspecification. All right, so let's say that we've got data that looks like this. Let's say it's a U-shaped pattern in the data. And you fit a straight line through there. Well, now you'll notice that the residuals are going to follow a pattern. So the residuals up to this point are above the line, and then here they are below the line, getting farther away, and then they turn around, they are still below the line, but they're getting closer, and then they go up above the line again. So if you know that that's the pattern, if you had an error term over here, and you knew that you'd sort of turned this corner and now you're heading back up towards the line, you have information that this next error term is going to be somewhere around here, and then after that the error terms will probably be above the line. So there's a specific pattern to the errors, and so that means they're not purely random anymore. So if they're purely random, it means that if you knew this error term and all the previous error terms, you still have no idea what the next error term will be. You would say, okay, given this residual and all the previous residuals, I have no idea if the next residual will be up here or it could be somewhere down there. Well, that's not a reasonable estimate. Given the pattern of the data, it looks like your next error term is going to be up there. So it's not purely random, and the fact that the previous values allow you to predict next period's error term means you've got autocorrelation. You've got some memory going in the process. Well, in that case, yes, it's autocorrelation, but it's also kind of obviously that the data is not following a linear pattern in the x's. And so what we would say here is your obvious solution, if that's what your data looks like, you should estimate, you should fit a curve through the data. So this was a regression of y equals a alpha plus beta x. If we do y equals alpha plus beta 1 x1 plus beta 2 x2 squared, so we're going to allow a quadratic equation, then you're going to end up with a fitted line that looks something like that. Well, now everything's changed, because now you've got error terms that really do fall on either side of the line in a more or less random pattern. So if I tell you, I give you that data point, and so you know that that's the error term at this point in the sample, even knowing the error terms back here doesn't guarantee that the next error term is going to be up here as well. It could actually be below the line. It could be anywhere in the range. So sometimes autocorrelation arises because you're fitting, in this case, a straight line through quadratic data. Sometimes the appearance of autocorrelation means you have a misspecified regression model. And in that case, now if for some reason you had to fit a straight line, you only want a linear regression, then okay, you still need to correct for the autocorrelation. You're just putting the structure of your explanatory model into the error term. But if there's nothing stopping you from fitting a quadratic model or even a cubic model, you could add an x cubed in here, as you will do in the assignment. Then that means you're putting the structure in the regression equation and leaving yourself a random error term that doesn't have any structure in it. If you understand the picture, if you can see the logic of the picture, the point here is what looks like autocorrelation in the error term may be telling you that you just need to have a richer explanatory model in the x's themselves, rather than just resorting to an autocorrelated error term. So that's all you need to do the assignment, and hopefully that's all you need to get through the chapter. And we only have one more topic in chapter 5 to work on, and we will tackle that next time.